3-Eye Atlas has just broken another rule. November's telescope images showed jets, multiple jets, extending over 1 million kilometers with no curvature, no rotational smear, no spreading. Razor straight, geometrically perfect, as if someone drew them with a ruler across space itself. But here's the problem. The object is spinning. Every 16 hours, it completes a full rotation. Those jets should spiral, twist, smear like water from a spinning sprinkler. They don't. They remain locked, stable, pointing in the same direction for weeks, while the object tumbles beneath them. Scientists are calling this 3-Eye Atlas's 12th anomaly, and some are no longer using the word comet. Stay with me, because by the end, you'll understand why this might be the most important object we've ever tracked. Picture this. It's November 8th, 2025. Two astronomers in Austria, Michael Jaeger and Gerald Riemann, are stacking telescope exposures of an object called 3-Eye Atlas, an interstellar comet that's been drifting through our solar system for months. They're expecting the usual fuzzy glow, maybe some diffuse jets of gas and dust spraying out as the sun warms its icy surface. Standard comet stuff, but when the stacked images resolve on their screens, they freeze. What they're seeing shouldn't exist. Stretching across the frame are jets, multiple jets, so razor straight they look like someone drew them with a ruler. Not curved, not fanned out, not smeared. Just perfectly linear beams of material extending over 1 million kilometers into space. That's roughly the distance from Earth to the Sun. And these jets are locked in orientation, pointing in the same direction across multiple nights of observation, despite the fact that 3-Eye Atlas is supposed to be rotating once every 16 hours. Let me explain why that's impossible. When a comet spins, anything ejected from its surface should spin with it. Imagine standing on a merry-go-round and spraying a garden hose. The water would arc and swirl, creating a spiral pattern. It wouldn't shoot out in a perfectly straight line, unaffected by your rotation. But that's exactly what 3-Eye Atlas is doing. The object is spinning. We measured its 16.16-hour rotation period earlier this year, yet its jets behave as if they're completely immune to that spin. The scale makes it even stranger. Material typically leaves a comet's surface at about 400 meters per second when ice sublimates into gas. At that speed, it would take roughly a month for particles to travel the full 1 million-kilometer length we're seeing in these images. So these jet structures aren't fleeting. They're persistent, stable, directionally locked for weeks at a time, while the nucleus beneath them completes dozens of rotations. Confirmation came the next night. Franz Niebling and Michael Buchner, two more observers, captured the same phenomenon. Multiple 3-minute exposures, stacked, and cross-validated. Same result. The jets remained collimated, astronomers' word for tightly focused, with no visible curvature, no rotational smear, no spreading out into fans. Just beams. This is now being called 3-Eye Atlas's 12th anomaly. The object has been racking them up since it was discovered. Unusual trajectory, strange composition, bizarre polarization signatures. But this one is different. This one makes even mainstream comet scientists go quiet. Because if these jets are real, and the evidence says they are, then something deeply weird is happening. Either we're looking at a comet that behaves unlike anything we've ever categorized, or we're looking at something that isn't a comet at all. What if this isn't sublimating ice responding to solar heat? What if these aren't natural outgassing plumes? What if, instead, we're watching directed thrust, controlled propulsion, emanating from an object that's crossed the interstellar void to visit our solar system? That question sits at the intersection of cosmic dread and wonder. And it's the question driving scientists, amateur astronomers, and anyone paying attention absolutely wild right now. Some researchers are calling this the most compelling technosignature candidate we've encountered since Oumuamua zipped through in 2017. Others are scrambling to salvage natural explanations, constructing elaborate models involving shadowed pockets of ice and phase-locked ejection cycles. But the models are straining. The data is pushing back. Over the next hour, we're going to unpack this observation from every angle. We'll walk through the evidence, what was seen, how it was measured, why it contradicts prior data. We'll explore the natural hypotheses, the ones that try to keep 3i Atlas firmly in the category of weird but explainable comet. Then we'll dive into the radical alternative, the one that asks whether we're witnessing something engineered. We'll examine what hidden physics or unknown mechanisms could produce these jets, and what the implications would be if they're artificial. And we'll connect this to the broader landscape of 2025 astronomy, where our tools are finally becoming sharp enough to catch phenomena that previously slipped past us unnoticed. But before we go there, sit with this image for a moment. Imagine you're the astronomer stacking those frames. You've done this 1,000 times. You know what comet jets should look like. And then your screen fills with structures that belong in a science fiction film. Geometric, persistent, defying rotation. You lean back in your chair. You check your calibration. You run the stack again. Same result. You send the images to colleagues. They confirm it, and suddenly you're holding evidence of something that shouldn't be possible. Something that forces you to question whether the object you've been tracking is what you thought it was. What else might we learn if this anomaly holds up under scrutiny? What will it force us to reconsider about the nature of comets, about interstellar objects, about what's out there moving through the dark? And if these jets are controlled, if they're evidence of technology, what does it mean that we're only noticing now, months after the object entered our system, when it's already preparing to leave? The observational campaign that revealed this anomaly wasn't some fluke backyard telescope snapshot. This was coordinated, rigorous work by experienced astrophotographers using serious equipment. On November 8th, Michael Jaeger and Gerald Riemann in Austria, along with Efrain Prosperi in Argentina, independently imaged 3i Atlas with multiple 3-minute exposures. The technique is called stacking. You take dozens of individual frames and layer them digitally, which cancels out random noise and brings out faint structures that would otherwise be invisible. It's how astronomers tease signal from chaos. When their stacks resolved, they revealed jet structures extending to distances exceeding 1 million kilometers. Not vague wisps, not diffuse clouds. Linear features, collimated to an almost laser-like degree, with no detectable curvature or spreading. The next night, Franz Niebling and Michael Buchner performed confirmatory imaging and got the same results. Cross-validation across multiple telescopes, different observers, different hemispheres. This wasn't instrumental artifact. This was real structure in the comet's coma. Now, let's talk about the rotation problem. Earlier in 2025, before these jet images emerged, astronomers performed light curve analysis on 3i Atlas. A light curve tracks how an object's brightness changes over time. If the object is irregularly shaped and rotating, its brightness will fluctuate as different facets catch sunlight. By measuring the periodicity of those fluctuations, you can determine the rotation period. For 3i Atlas, the answer came back clear: 16.16 hours, with an uncertainty of only 0.01 hours. Solid measurement. The object is spinning, completing a full rotation roughly twice per Earth day. Here's where the contradiction bites. If 3i Atlas is rotating every 16 hours, and material is being ejected from its surface, that material should inherit the rotation. Picture a figure skater spinning and throwing confetti. The confetti doesn't fly out in straight lines. It spirals. It fans. It traces the rotational motion. Comet jets normally show exactly this kind of smearing. When the Rosetta spacecraft orbited Comet 67P, it watched jets curve and sweep as the nucleus rotated beneath them. That's normal. That's physics. But 3i Atlas's jets don't curve. They don't sweep. They remain fixed in orientation across multiple rotations, as if locked in place by some external force or internal mechanism that overrides the spin. The material travels at an estimated 400 meters per second, typical for volatile sublimation, solid ice turning directly into gas under solar heating. At that velocity, a particle takes roughly 30 days to traverse the million-kilometer length visible in the images. So the jet structure must persist for weeks, maintaining its collimation and directional stability while the nucleus beneath it completes hundreds of rotations. There's no precedent for this in solar system comets. Jets can be narrow, sure, Some comets have active vents that produce concentrated plumes, but those plumes rotate with the nucleus. They sweep across the sky like lighthouse beams. They don't remain stationary, while the source spins underneath. Another wrinkle: the orientation of some jets doesn't align with the sunward direction. Normally, comet jets are driven by solar heating. The sun warms one side of the nucleus, ice sublimates, and gas and dust spray outward from the heated region. You'd expect jets to point roughly away from the sun, maybe with some deviation due to topography or rotational lag, but at least some of 3I Atlas's jets point in directions that don't correlate with solar illumination angles. That undermines the simple sun-driven outgassing model. If the sun isn't heating those regions, why are they active? So we're left with a stark set of possibilities. Either the nucleus has somehow stopped rotating, or slowed dramatically, since the 16-hour period was measured, or the jets are phase-locked by some mechanism we don't understand, ejecting material in precisely timed pulses that stack up into stable beams. Or the jets aren't natural outgassing at all, but something else entirely. The problem is, we don't have a recent rotation measurement post-November images. The light curve data is months old. It's possible, though strange, that something changed. Maybe a massive outgassing event altered the nucleus's angular momentum. Maybe tidal forces or internal structural shifts slowed the spin. But those are ad hoc explanations, patches applied to save the comet hypothesis. And they raise more questions than they answer. The evidence itself is robust. Multiple independent observers, stacked exposures to enhance signal, cross-validation across different instruments and locations. The jet structures are real. The contradiction with prior spin data is real, and the scale is enormous, making this one of the most geometrically precise and physically puzzling comet phenomena ever recorded. If you're an astronomer who's spent decades studying comets, this is the kind of observation that makes you want to throw your textbooks out the window and start from scratch. So, what could be causing it? What natural mechanisms might produce collimated, rotationally stable jets that ignore the sun's influence? That's the question we're turning to next. And I'll warn you now, the answers get uncomfortable. Let's try to save the natural explanation first. Let's assume 3I Atlas is just a comet, an unusual one, granted, but still a comet, and figure out how it could produce these jets without invoking anything exotic. Scientists have proposed several models, each attempting to reconcile the observations with known physics, but each model strains under scrutiny. The first is called deep pocket sublimation. The idea is that 3I Atlas has pockets of volatile ices, carbon dioxide, carbon monoxide, maybe water, buried beneath layers of dust or rock. These pockets only sublimate when illuminated at very specific angles. Imagine a cavity on the nucleus's surface, oriented such that sunlight reaches it only during a narrow window of each rotation. When the sun hits, ice turns to gas, pressure builds, and a concentrated jet erupts. The rest of the time, the pocket remains in shadow and inactive. If multiple pockets are aligned in similar orientations, they could produce jets that appear directionally stable because they only fired during the same phase of rotation. It's clever. It could explain why the jets seem locked in place. But it struggles with the scale and persistence. For this model to work, the pockets would need to be enormous, capable of sustaining outflow for weeks, and they'd need to be oriented with extraordinary precision, all pointing in nearly the same direction, all activating in perfect synchrony. That's a lot of coincidences. There's also the peas in a pod model, which tries to explain the jet's appearance by invoking pulsed ejection. If material is ejected in discrete bursts once per rotation, then over many rotations, those bursts would form a trail of peas, clumps of material spaced along the jet path. The spacing would be the distance traveled in one rotation period. At 400 meters per second and 16.16 hours, that's about 23,000 kilometers between each clump. When you stack telescope exposures over multiple nights, the individual clumps blur together, creating the illusion of a continuous, stable jet. This model has mathematical elegance. It preserves rotational mechanics while producing the observed structures. But here's the problem. If the jets were made of discrete clumps, we should see brightness variations along their length. Some exposures should catch the clumps in different positions, creating gaps or uneven intensity. The images don't show that. The jets appear smooth and continuous. And again, this model doesn't explain jets pointing away from the sun. If ejection is triggered by solar heating, why are there active regions on the night side? Let's zoom out and look at 3i Atlas's other anomalies, because they compound the pressure on natural explanations. Spectroscopic observations by the James Webb Space Telescope earlier in 2025 revealed that the comet's coma is dominated by carbon dioxide, with a carbon dioxide to water ratio of about 8:1. That's much higher than typical solar system comets, which are usually water-rich. It suggests 3i Atlas formed in a colder, more carbon dioxide-rich environment than the comets we're used to. Possible, but unusual. Then there's the polarimetry. When sunlight reflects off dust particles in a comet's coma, it becomes polarized. The degree of polarization changes with the phase angle, the angle between the sun, the comet, and the observer. Most comets follow a predictable pattern. 3i Atlas doesn't. It exhibits a very deep negative polarization branch, reaching -2.7% at a phase angle of about 7 degrees. That's unprecedented among known comets and asteroids. It suggests the dust particles in its coma have unusual optical properties, possibly a unique composition or structure. Now add the trajectory. 3i Atlas is on a retrograde orbit, meaning it's moving opposite to the direction most solar system objects travel. That's expected for an interstellar interloper. But its orbital plane is aligned to within about 5 degrees of the ecliptic, the plane where Earth and most planets orbit. The probability of an interstellar object arriving with that alignment by chance is roughly 0.2%, 1 in 500. Not impossible, but statistically unlikely. Each of these features, taken alone, can be explained away. High carbon dioxide, formed in a different stellar environment. Strange polarization, exotic dust grains, ecliptic alignment, cosmic coincidence. But when you stack them, pun intended, the cumulative oddness starts to feel uncomfortable. It's like meeting someone who's left-handed, red-haired, born on a leap day, and shares your birthday. Any single trait is rare, but plausible. Altogether, you start wondering if something else is going on. And that's before we get to the jets. The jets are the anomaly that breaks the camel's back. They don't just stretch plausibility. They shatter it. Because maintaining collimated, rotationally stable, non-solar aligned jets over weeks requires physics we don't have a good handle on. Maybe there's some unknown topographical or magnetic effect. Maybe the nucleus has internal structure that channels outgassing in bizarre ways. Maybe we're missing something fundamental about how interstellar comets behave. Or maybe, and this is where the conversation gets dangerous, 3i Atlas isn't a comet at all. Maybe the natural hypothesis is wrong. Maybe we're looking at something engineered, something designed to produce those jets, something that entered our solar system with intent. That's the possibility we're turning to next. And whether you find it thrilling or terrifying probably says a lot about how you feel standing at the edge of the unknown. Avi Loeb doesn't mince words. The Harvard astrophysicist who championed the idea that Oumuamua might be artificial has turned his attention to 3i Atlas, and he's saying what a lot of people are thinking, but few are willing to say publicly. This might not be a comet. It might be a probe, an alien spacecraft, a piece of technology from another civilization coasting through our solar system on a trajectory that just happens to bring it close enough for us to notice. Loeb's argument hinges on the jets. If they're straight, stable, and directionally locked despite rotation, then they're behaving like controlled thrust, like thrusters maintaining orientation, rather than random natural plumes. Imagine a spacecraft using ion engines or plasma jets to adjust its course or orientation. The exhaust would be collimated, persistent, and unaffected by the craft's spin if the thrusters themselves are gimbal-mounted or electronically stabilized. That's exactly the behavior we're seeing. When human spacecraft need to maintain a specific orientation, say keeping solar panels pointed at the sun while the craft tumbles for thermal stability, they use reaction control systems that fire in precise directions regardless of overall rotation. The jets from 3i Atlas look disturbingly similar to that kind of controlled emission. Loeb points out that the persistence is particularly telling. Natural comet jets flicker, vary in intensity, respond to changing solar illumination as the nucleus rotates. They're temperamental, driven by the chaotic process of ice sublimating unevenly across a spinning, irregularly shaped surface. But 3I Atlas's jets remain stable for weeks, maintaining their geometry and direction through dozens of rotation cycles. That kind of consistency suggests regulation, control, feedback mechanisms that adjust output to maintain desired parameters. It's the signature of engineering, not randomness. He's not alone in floating this idea. Other researchers have noted the accumulation of anomalies and suggested that 3I Atlas deserves serious consideration as a technosignature candidate. The Loeb scale, a proposed ranking system for assessing the likelihood that an object is artificial, would place 3I Atlas relatively high if the jet behavior holds up under further scrutiny. The scale runs from 0, clearly natural, to 10, which would be unambiguous artificial technology, like a visible spacecraft with running lights and radio transmissions. 3I Atlas sits somewhere around a 5 or 6 on this scale. It's not at the top. Nothing short of receiving a radio message or detecting manufactured materials would push it there, but it's above the noise floor. It's in the "this warrants serious investigation" tier, the range where you can't dismiss the possibility without looking foolish if it turns out to be real. Let's list the features that might support an engineered origin. First, obviously, the jets themselves. Straight, stable, non-rotational, non-solar aligned. They're the headline anomaly, the thing that started this whole conversation. Second, the trajectory. 3I Atlas is on a retrograde orbit, meaning it's moving opposite to the direction most solar system objects travel, and that orbit is aligned to within about 5 degrees of the ecliptic plane. For context, most interstellar objects should arrive from random directions, because there's no preferred orientation in interstellar space. The ecliptic alignment could indicate intentional navigation rather than random arrival. If you wanted to survey a planetary system efficiently, you'd approach along the plane where the planets orbit, maximizing your exposure to interesting targets while minimizing fuel expenditure for course corrections. Third, the composition. Low water, high carbon dioxide, unusual dust properties that produce anomalous polarization. If you were designing a spacecraft and wanted it to masquerade as a comet for observational cover, maybe to avoid triggering defensive responses from any civilizations you encountered, you might engineer a coma with exotic chemistry to confuse spectroscopy. You'd use materials that sublimate under solar heating, producing a genuine comet-like appearance, while the underlying structure remains hidden beneath the outgassing. The coma becomes camouflage, a cloud of particles and molecules that obscures what's really there. Fourth, the object's mass and velocity. 3I Atlas is more massive than most interstellar objects we've detected, and moving faster than expected for something that's simply fallen into our system from the interstellar void. That could suggest onboard propulsion, either active now, explaining the jets, or expended earlier in its journey, giving it a higher velocity than it would have from gravitational interactions alone. The mass estimate comes from modeling how much material needs to be present to produce the observed brightness and outgassing. If 3I Atlas were hollow, like a manufactured shell, the mass estimate would be too high. But we can't tell from current observations whether it's solid or hollow, natural or engineered. There's also the timing, which gets into slightly paranoid but not entirely absurd speculation. 3I Atlas entered our solar system at a point where human observational capabilities are sharp enough to notice anomalies, but not yet advanced enough to decisively analyze them. We can see the jets, measure their properties, detect radio emissions, perform spectroscopy, but we can't yet image the nucleus at high enough resolution to see surface details, can't send a probe to intercept it, can't determine definitively whether it's natural or artificial. If you were an alien probe programmed to survey stellar systems, you might time your flyby to occur during a civilization's early observational period, when they're aware enough to detect you, but primitive enough that you don't pose a threat or have the capability to interfere with your mission. You'd reveal yourself just enough to be noticed, then leave before they could respond. Speculative? Sure, but not irrational given what we know about the progression of technological capabilities. Now, let's steelman the opposition, because there are plenty of skeptics, and they have good points. Jason Wright, an astronomer at Penn State who specializes in technosignatures and has spent years thinking about how to distinguish artificial from natural phenomena, has argued that every single anomaly attributed to 3I Atlas is still within the bounds of natural variability. Strange jets? Comets can be weird. We've only studied a few hundred comets up close, out of trillions that exist. Sampling bias means we might be seeing normal interstellar comet behavior and mistaking it for anomalous simply because we've never observed an interstellar comet this thoroughly before. Odd composition? Interstellar comets formed in different stellar environments, around stars with different metallicities and different protoplanetary disk chemistries. Of course, they'll have exotic compositions compared to solar system comets. That's expected, not surprising. Ecliptic alignment? Rare, but not impossible. With thousands of interstellar objects passing through the solar system over millions of years, most undetected, eventually one will arrive with an unusual trajectory, by pure chance. We notice it precisely because it's unusual, but that doesn't make it artificial. It's selection bias. We're paying attention to 3I Atlas because it's weird, but weirdness alone doesn't equal engineering. Wright and others caution that calling it a spacecraft distracts from legitimate comet science and sets the public up for disappointment when natural explanations eventually prevail. They've seen this cycle before with Oumuamua, where initial excitement about artificial origins gave way to more mundane explanations involving outgassing-driven acceleration and unusual shapes. Fair enough. Extraordinary claims require extraordinary evidence, and right now we have extraordinary observations, but not yet extraordinary proof. The jets could be natural, even if we don't fully understand the mechanism producing them. The composition could reflect exotic formation conditions rather than engineering. The trajectory could be a statistical fluke, one of those rare events that becomes inevitable given enough opportunities. And the mass and velocity could simply indicate we're still calibrating our models for interstellar objects, learning what's normal for visitors from other stellar neighborhoods. But here's the emotional core of this debate, the reason it generates such intense reactions from scientists and the public alike. If 3I Atlas is artificial, we're witnessing the first unambiguous evidence of extraterrestrial engineering in our solar system. The first time in human history. The moment that rewrites history, redefines our place in the cosmos, and confirms we're not alone. It would be the most important discovery ever made, eclipsing every other scientific achievement, because it would prove that intelligence, technology, and the drive to explore exist elsewhere. It would mean other civilizations have mastered interstellar travel, built machines capable of crossing light years, and sent them to survey or study other stellar systems. It would raise immediate questions about their intentions, their capabilities, their awareness of us, and what our response should be. If it's not artificial, we're still facing a natural object that stretches our understanding of comets to the breaking point, forcing us to expand our models and rethink what's possible in the interstellar medium. We'd learn that comet physics is far richer and stranger than our solar system-centric view suggests. We'd discover new mechanisms for collimating jets, new compositions that produce unusual behaviors, new formation environments that create objects unlike anything in our cosmic backyard. That's still profound. That still advances science significantly, but it doesn't carry the existential weight of confirming extraterrestrial intelligence. So the stakes are asymmetric. One answer changes everything about how we see ourselves and our place in the universe. The other answer expands our scientific knowledge substantially, but leaves the big questions unanswered. That asymmetry drives the intensity of the debate and the emotional investment people have in the outcome. Think of it like seeing a contrail behind an airplane at 30,000 feet. If you lived in a pre-industrial society and saw that white streak cutting across the sky, perfectly straight, persisting for minutes, you'd be baffled. Natural explanations, clouds, ice crystals, wind patterns, wouldn't quite fit. Clouds don't maintain that kind of geometric precision. Ice crystals don't follow moving sources. The straightness, the persistence, the way it tracks across the sky in a line, all point to something creating it deliberately. Eventually, you'd have to consider the possibility that something artificial is producing it, even if that idea seemed absurd given your prior experience of the world. You'd have no framework for understanding jet engines or aircraft, but you'd recognize that natural phenomena don't behave that way. That's where we are with 3i Atlas. The straight jets are our contrail, and we're trying to decide whether to expand our meteorological models, our understanding of comet physics, or entertain the possibility that something built them. We're in that pre-industrial society looking at the sky, seeing something that doesn't fit, and debating whether to invoke new natural laws or accept that we're witnessing technology from a civilization that's mastered capabilities we haven't yet achieved. The debate will continue. More data will accumulate. Observations will either support the natural hypothesis by revealing mechanisms that explain the jets, or they'll push toward the artificial hypothesis by ruling out natural alternatives one by one. Either outcome teaches us something fundamental, but only one outcome answers the question we've been asking since we first looked up at the stars and wondered if anyone else was out there looking back. Next, we're going to explore what kind of physics or architecture would allow those jets to behave the way they do. If they're natural, what unknown mechanisms might be at play? If they're engineered, what technologies could produce them? And what would it mean for our place in the cosmos if the answer turns out to be the latter? Let's start with the natural side. If 3i Atlas's jets are produced by sublimation and outgassing, how could they remain collimated and rotationally stable? What physics are we missing? One possibility involves magnetic fields. Some comets have been observed to generate weak magnetic fields, either through ionization of outflowing gas or interaction with the solar wind. If 3i Atlas has an unusually strong internal or induced magnetic field, it could channel ionized particles along field lines, producing jets that remain fixed in orientation relative to the field rather than the rotating nucleus. This happens in astrophysics. Black holes and young stars produce jets that stay collimated for light years because magnetic fields act like invisible nozzles, focusing the outflow. Maybe 3i Atlas is doing something similar on a smaller scale. Another option is self-stabilizing geometry. Imagine the nucleus has deep canyons or vents with specific shapes that naturally collimate outflow. The gas accelerates through narrow channels, creating high-velocity beams that resist spreading. If multiple vents are aligned by chance or by the object's internal structure, they could produce the observed jet pattern. It's like how a rocket nozzle focuses exhaust into a tight stream rather than letting it expand in all directions. Maybe 3i Atlas has natural nozzles, or consider material strength and internal architecture. If the nucleus is unusually cohesive, held together by tensile strength rather than just gravity, it might support structures that channel gas in precise directions. Some models of interstellar objects suggest they could be fractal aggregates, clumps of smaller bodies loosely bound together. If 3i Atlas has that kind of internal structure, gas could percolate through it in complex ways, emerging in concentrated jets. These are plausible but speculative ideas. They require 3i Atlas to have properties we haven't confirmed and processes we haven't observed. They're not impossible, but they're stretching the natural framework pretty hard. Now let's flip to the engineered scenario. If 3i Atlas is artificial, what technologies could produce these jets? The most straightforward answer is controlled propulsion. Imagine a probe equipped with adjustable thrusters, ion engines, plasma drives, or some propulsion system we haven't invented yet. The thrusters are mounted on gimbals or actuators that allow them to stay oriented in a fixed direction regardless of the probe's rotation. This is exactly how human satellites maintain attitude control. They spin for stability, but their thrusters or reaction wheels keep specific directions locked relative to external references, like stars or planets. If 3i Atlas is using this kind of system, the jets we're seeing could be exhaust plumes from course correction burns or orientation adjustments. The fact that some jets don't point sunward could indicate they're not driven by solar heating, but by onboard fuel, maybe nuclear, maybe chemical, maybe something exotic. The straightness and persistence would be signatures of deliberate control rather than chaotic natural outgassing. The composition fits this scenario too. High carbon dioxide, low water, unusual dust. If you're designing a spacecraft and need a coma for camouflage, or for radiation shielding, or for some other functional purpose, you'd engineer the chemistry to suit your needs. You wouldn't necessarily mimic solar system comets because you're not from here. Your coma would reflect the materials and technologies available in your stellar neighborhood. Let's talk probabilities. We've already mentioned the ecliptic alignment, 5-degree inclination, 0.2% chance. Add the retrograde orbit, which narrows the arrival geometry. Add the velocity and mass, both atypical for interstellar objects. Add the composition anomalies, the polarization signature, the non-solar aligned jets, and the rotational paradox. Each anomaly individually has a low but non-zero probability. Multiply them together, and you're approaching improbabilities that demand explanation. This is where philosophy enters. When does cumulative oddness justify abandoning the default hypothesis? In science, we use Occam's razor. The simplest explanation is usually correct, but Occam's razor assumes the simplest explanation is natural, which works fine when you're comparing natural hypotheses. It breaks down when you're comparing a strained natural explanation against a straightforward artificial one. If the natural model requires 7 ad hoc assumptions and the artificial model requires 1, something built this, which is actually simpler. Epistemologically, we're in tricky territory. Our prior for alien spacecraft is extremely low because we've never confirmed one. So we demand overwhelming evidence. But we also risk dismissing genuine technosignatures because our priors are so skewed. It's the classic detection problem. You can't find what you're not willing to look for. If 3i Atlas is natural but extreme, it tells us interstellar space can produce comet behaviors we didn't anticipate. New categories, new formation environments, new chemical inventories. That's exciting. It expands the taxonomy of cosmic objects and enriches our understanding of planetary system formation in other stellar environments. If it's engineered, the implications detonate outward. Extraterrestrial intelligence exists. They build things. They travel between stars. They've entered our solar system, possibly multiple times, which raises immediate questions. Are they observing us? Are they oblivious to us? Did they arrive recently, or have they been here, dormant or inactive, for millennia? How many others are out there? What do they want? Imagine a timeline where 3i Atlas, or something like it, arrived millions of years ago, drifted through the Oort cloud, and only now passed close enough for us to notice. What are the odds we'd catch it during the brief window when it's active and visible? Tiny, which suggests either we're extraordinarily lucky, or there are many such objects, and we're only now developing the tools to see them. Observationally, the next steps are clear. Measure the rotation period again. If it's slowed or stopped, that's huge. If it hasn't, the jets become even more baffling. Use high-resolution imaging to examine the nucleus's shape and surface features. Look for structure that might explain collimated outflow. Conduct spectroscopy of the jets themselves to determine composition and velocity gradients. Search for radio or infrared emissions that might indicate onboard power sources or waste heat. And track 3i Atlas as it leaves the solar system. If it accelerates or changes trajectory in ways that can't be explained by gravity or outgassing, that's a smoking gun. Whether natural or engineered, 3i Atlas is forcing us to reconsider our assumptions. Comets might be stranger than we thought. Interstellar objects might carry signatures of alien technology. Our solar system might be crossed regularly by things we've been calling comets when they're something else entirely. And in the final sections, we're going to step back and look at what else is happening in astronomy and technology right now. Developments that connect to this story and suggest we're on the cusp of answering questions we've been asking for centuries. While the world was buzzing about 3i Atlas's mysterious jets, another breakthrough quietly reshaped how we study interstellar visitors. In October 2025, astronomers using South Africa's Meerkat radio telescope detected the first ever radio signals from an interstellar object. The target was 3I Atlas. The signal wasn't artificial. It was natural, but it was unprecedented, and it gave us a new lens for understanding what this object is and isn't. Radio telescopes don't capture visible light. They detect electromagnetic radiation at much longer wavelengths, the kind emitted by certain molecules when they're energized. One of those molecules is hydroxyl, the OH radical, which forms when ultraviolet sunlight breaks apart water molecules. As comets approach the sun and their ices sublimate, water vapor floods the coma. Solar UV photons smash those water molecules, producing hydroxyl radicals that emit radio waves at a specific frequency, 1.667 gigahertz. This emission has been detected from solar system comets for decades, but never before from an object that originated beyond our stellar neighborhood. When Meerkat pointed at 3I Atlas, it detected that signature. Strong, clear, unambiguous. Hydroxyl emission, consistent with water breakdown. This was the first time a radio telescope had caught such a signal from an interstellar comet, and it confirmed something important. 3I Atlas is outgassing volatiles, specifically water, even though spectroscopy shows its coma is carbon dioxide dominated. The water is there, just in lower abundance than typical solar system comets. The detection required hours of integration time, stacking radio observations the same way optical astronomers stack images, pulling signal out of cosmic noise until the 1.667 gigahertz line emerged unmistakably. Why does this matter? Because it supports the natural comet hypothesis. If 3I Atlas were entirely artificial, a metal spacecraft with no volatiles, it wouldn't produce hydroxyl emission. The fact that it does means there's real sublimation happening, real ices turning into gas, real comet activity driven by solar heating. That doesn't rule out an engineered origin entirely. Maybe the probe has an icy shell for shielding or camouflage. Maybe it's using ablative materials that mimic comet outgassing, but it narrows the parameter space. It makes the purely artificial scenario less likely. Unless, of course, the engineers specifically designed it to look like a comet in every observable way, which opens a whole different can of speculative worms. At the same time, the detection is scientifically thrilling beyond the implications for 3I Atlas's nature. Meerkat is part of a new generation of radio arrays designed for deep sky surveys and precision measurements. It's a precursor to the Square Kilometer Array, which will be the most sensitive radio telescope ever built once it's complete. The fact that we can now listen to comets in radio, not just watch them in visible or infrared, opens up new diagnostic tools. We can measure outflow rates by tracking hydroxyl intensity over time. We can map the spatial distribution of water vapor in the coma. We can monitor activity in real time, even when the comet is too faint or too far for optical telescopes to resolve clearly. Radio observations also pierce through dust that obscures optical wavelengths, giving us access to regions deep within the coma where particles would normally block our view. And because hydroxyl emission traces water specifically, it provides a direct measurement of one of the most important volatile components, bypassing the ambiguities that come from interpreting reflected sunlight or thermal infrared glow. This ties directly to the broader theme. Our observational capabilities are exploding. 20 years ago, we wouldn't have detected 3I Atlas at all. It would have passed through unnoticed, just another faint smudge against the background stars, too dim and distant to trigger automated alerts. 10 years ago, we might have noticed it, but missed the jets, lacking the image stacking, techniques, and cross-observatory coordination that revealed their structure. 5 years ago, we'd have seen the jets but couldn't confirm their stability or rule out instrumental artifacts, unable to validate the observations across multiple telescopes and wavelengths. Today, we have stacking algorithms refined by processing billions of astronomical images. We have cross-validation across global networks where observers on different continents confirm each other's findings within hours. We have spectroscopy from space telescopes like James Webb that can fingerprint molecules with stunning precision. And now we have radio confirmation of molecular outflow, adding another independent line of evidence. We're finally catching up to the phenomena that have always been out there, invisible to our earlier instruments, waiting for us to develop the technology to see them. The hydroxyl detection also raises a question. Does it weaken the case for 3i Atlas being artificial? Yes and no. It confirms volatile outgassing, which fits the Comet model beautifully. Water ice exposed to sunlight sublimates predictably. UV radiation breaks it down into hydroxyl and hydrogen predictably. The emission frequency matches laboratory measurements predictably. Everything about the radio signal screams natural Comet process, but it doesn't explain the jets. You can have water sublimation and still have collimated rotationally stable jets if there's an underlying mechanism, natural or engineered, that channels the outflow. The radio signal tells us what's coming out, not how it's being directed. So the radio signal refines the picture without settling the debate. It constrains the models, rules out some extreme scenarios, but leaves the central mystery intact. Think of it like hearing an engine sound from an object in the distance. The sound tells you there's combustion happening, energy being released, gases expanding. That suggests a machine of some kind, but it doesn't tell you whether the machine is natural, like a geothermal vent hissing steam and sulfur compounds, or artificial, like a car engine burning gasoline. You need more data. You need to see the object, measure its geometry, analyze the exhaust composition in detail, check for control systems or navigation. That's where we are with 3i Atlas. The radio signal is a clue, not a conclusion. It's a data point that narrows possibilities but doesn't eliminate the fundamental question. And it's not just radio. Other instruments are coming online in a coordinated surge that feels almost timed for this moment. The James Webb Space Telescope continues to provide infrared spectroscopy with unprecedented resolution, revealing molecular abundances that earlier missions could only dream of measuring. Ground-based optical networks are coordinating observations across continents, pooling data through automated pipelines that flag anomalies in near real time. AI algorithms are being trained on millions of astronomical images, learning to detect patterns and oddities that human observers might miss or dismiss. These systems can process more data in an hour than a team of astronomers could analyze in a year, flagging objects that don't fit known categories and routing them for detailed follow-up. We're building an observational infrastructure that will make the next 3i Atlas impossible to miss and much easier to analyze. When the next interstellar visitor arrives, and statistically, another should enter the inner solar system within a few years, it will be detected earlier, tracked more thoroughly, and examined across every wavelength from radio to gamma rays. We'll have its light curve, rotation period, spectrum, morphology, and outgassing rate within days instead of months. And if it shows anomalies, we'll know immediately. So does the radio detection settle things? Not even close. It adds a piece to the puzzle, confirms some hypotheses, complicates others. It shows us that even when we get new data, the mystery doesn't vanish. It just gets more textured, more interesting, more demanding of further investigation. Each answer spawns 3 new questions. Why is the water abundance so low compared to carbon dioxide? Why does hydroxyl emission confirm outgassing, but the jets still defy rotational expectations? What other molecules are we missing because we haven't looked at the right wavelengths yet? And that's exactly the kind of science that keeps people awake at night, staring at telescope data, wondering what they're really looking at. The Meerkat detection also validates a prediction. If interstellar comets behave fundamentally like solar system comets, just formed elsewhere with different compositions, then they should produce the same observable signatures when subjected to the same physics. Hydroxyl emission from water breakdown is one of those universal signatures. The fact that we detected it means the underlying chemistry works the same way across interstellar distances. Water is water. Ultraviolet photons are ultraviolet photons. The laws of physics don't change when you cross into another star system. That's reassuring in a way, grounding the mystery in familiar processes, even as the bigger picture remains unsettled. Next, we're going to explore the technology side, because as our ability to detect anomalies improves, so does our ability to create them. And the line between what we call natural and what we call artificial is getting blurrier. While astronomers were tracking 3i Atlas, engineers on Earth were pushing the boundaries of propulsion technology in ways that eerily mirror the phenomena we're debating in space. In 2025, experimental plasma sails and advanced ion drives have moved from theory to testing, demonstrating controlled thrust mechanisms that produce collimated exhaust plumes, exactly the kind of behavior that's making 3i Atlas so controversial. Take the recent European Space Agency. Experiment with magnetically accelerated plasma propulsion. The system uses superconducting magnets to channel ionized particles into tightly focused beams, achieving specific impulses far beyond chemical rockets. The exhaust is straight, stable, and can be vectored, redirected electronically, without moving the entire spacecraft. When engineers ran ground tests in vacuum chambers, the plasma jet stretched meters with no visible spreading, locked in direction despite the test rig's rotation. Sound familiar? Or consider NASA's ongoing work with variable-specific impulse magnetoplasma rockets, which can adjust thrust and exhaust velocity on the fly. These engines are designed for deep space missions, where efficiency and control are paramount. They produce exhaust that looks, in imagery, remarkably comet-like, glowing trails of ionized gas extending behind the spacecraft. If you didn't know it was artificial, you might mistake it for a natural phenomenon. The point is, we're developing technologies that blur the line between what looks natural and what's engineered, and that cuts both ways. On one hand, it gives us a roadmap for recognizing artificial behavior in objects like 3i Atlas. If we see jet characteristics that match known propulsion systems, that's suggestive. On the other hand, it complicates interpretation. Maybe natural processes can produce similar effects, and we're only now realizing it because our own technology is mimicking those processes. There's also the AI revolution in astronomy. Machine learning algorithms trained on millions of telescope images can now identify anomalies faster and more reliably than human observers. In 2025, an AI system scanning archival Comet data flagged several older objects with jet behaviors similar to 3i Atlas's, objects that had been dismissed as imaging artifacts or ignored because they didn't fit expectations. Turns out the anomalies were real, just unnoticed. The AI is teaching us to see what we've been missing. This has profound implications for technosignature searches. If AI can detect subtle patterns that indicate non-standard behavior, it can sift through decades of astronomical data and flag candidates that might be artificial. Or it can identify natural phenomena that were previously invisible, expanding our catalog of what's possible without invoking extraterrestrial engineering. Either outcome pushes science forward, but it also means the next 3i Atlas, or the next 100 of them, won't slip past us unnoticed. Consider the observational horizon. The Vera Rubin Observatory, which achieved first light in late 2024, is now conducting its legacy survey of space and time, imaging the entire visible sky every few nights. It's designed to catch transient events, supernovae, asteroid close approaches, anything that changes or moves. Interstellar objects entering the solar system will trigger automated alerts within hours of detection. We'll see them earlier, track them longer, and gather far more data than we did with Oumuamua or 3i Atlas. The James Webb Space Telescope continues delivering spectroscopy that reveals molecular fingerprints in comet comas with exquisite precision. Future instruments, like the Nancy Grace Roman Space Telescope, will add infrared imaging capabilities that can detect faint thermal emissions from distant objects. Ground-based interferometers are achieving resolutions that can resolve surface features on nearby asteroids and comets. The European Extremely Large Telescope, expected to be fully operational within a few years, will image exoplanets directly and study their atmospheres for biosignatures. If applied to solar system targets, it could potentially resolve structures on objects like 3i Atlas that are currently too small to see. All of these tools are converging toward a singular capability. We're approaching the threshold where we can definitively determine whether an anomalous object is natural or artificial. We can measure rotation with precision. We can map surface topography. We can analyze jet composition in real time. We can detect non-gravitational accelerations with enough accuracy to distinguish between outgassing and propulsion. We can search for electromagnetic emissions that might indicate onboard power sources. We can even look for heat signatures that don't match solar heating models. Within a decade, maybe less, the question of whether 3i Atlas is engineered won't be speculative. It will be answerable. We'll have the data. The challenge will be interpreting it honestly, without bias toward either the natural or artificial hypothesis, and accepting whatever the evidence tells us. There's a parallel here with the search for extraterrestrial intelligence more broadly. For decades, SETI focused on radio signals, scanning millions of frequencies for patterns that might indicate intentional transmission. That search continues, but it's expanded. Optical SETI looks for laser pulses. Technosignature surveys search for industrial pollution in exoplanet atmospheres or megastructures around distant stars. And now, with objects like 3i Atlas, we're asking whether interstellar visitors might themselves be technosignatures, probes, derelict spacecraft, or even active missions passing through. The technologies we're developing to answer that question are dual use. Propulsion systems that could take us to other stars also help us recognize artificial propulsion when we see it elsewhere. AI that finds anomalies in astronomical data could find anomalies in our own spacecraft telemetry, improving mission reliability. Spectroscopy that reveals alien chemistry teaches us about planet formation and the diversity of cosmic environments. Every tool we sharpen for detection also deepens our understanding of the natural universe. And that's the beautiful tension at the heart of this story. We're searching for the extraordinary while simultaneously expanding our definition of the ordinary. Each time we find something baffling, like 3i Atlas's jets, we face a choice. Do we assume it's natural and stretch our models to accommodate it? Or do we entertain the possibility that it's artificial and accept the profound implications? Science demands we consider both, hold them in tension, and let the evidence decide. Given where we are today, what would it actually take to prove 3i Atlas is artificial? A few things. First, unambiguous non-gravitational acceleration that can't be explained by outgassing. If the object speeds up or changes course in ways that require more force than sublimation can provide, that's a red flag. Second, electromagnetic emissions at frequencies or patterns inconsistent with natural processes, radio signals with structure, infrared heat sources that don't match solar heating, anything that suggests onboard energy generation. Third, surface features visible in high-resolution imaging that indicate manufacturing, geometric patterns, symmetry, materials with optical properties unlike natural minerals. We're not there yet, but we're closer than we've ever been. And the next interstellar visitor might arrive while our instruments are ready, our algorithms are trained, and our willingness to ask uncomfortable questions is finally strong enough to handle the answers. So, where does that leave us? With 3i Atlas currently receding from the sun, its jets still blazing, its mysteries unresolved, with a scientific community divided between those who see a comet pushed to its behavioral limits and those who see something else entirely, with technologies on Earth that increasingly mirror the phenomena we're debating in space, and with a future where the boundary between natural and artificial, between cosmic coincidence and extraterrestrial intent, is about to become testable in ways our predecessors could only dream of. We started this journey with a shocking image: razor-straight jets defying rotation, stretching across 1,000,000 kilometers, locked in place like beams from an impossible lighthouse. We've walked through the evidence, examined the hypotheses, entertained the speculation, and connected it to the broader currents of 2025 astronomy. We've asked what if. We've explored what it would mean. And we've stood at the edge of a question that might define our generation. Are we alone, or are we being visited by something that crossed the interstellar void to reach us? In a few years, when the next object like 3i Atlas appears, and it will, we won't just see it. We'll measure it, decode it, and understand it in ways that are currently impossible. That future is being built right now, telescope by telescope, algorithm by algorithm, observation by observation. And when it arrives, the mystery won't just deepen, it will resolve. One way or another, we'll know. The real question is, what will we do with that knowledge? How will we respond when the data finally, definitively, tells us whether we're looking at a comet or a craft? Whether we're witnessing natural physics at its most extreme or artificial engineering crossing our solar system, whether the universe is stranger than we imagined or populated in ways we've only written about in fiction. 3i Atlas won't answer those questions alone, but it's opened the door. It's forced the conversation. It's made the possibility real enough that scientists are taking it seriously. Instruments are being pointed, and resources are being allocated. The 12th anomaly might not be the last. It might just be the beginning of a cascade of discoveries that rewrite what we thought we knew about comets, about interstellar space, about who else is out there building things and sending them across the dark. So keep watching the sky. Keep asking questions. Keep demanding evidence while staying open to answers that challenge every assumption. Because somewhere out there, between the stars, things are moving. Some of them are ice and rock, following gravity's patient mathematics. And some of them, maybe, possibly perhaps, are something else. Something that sees us. Something that built the jets we're still trying to explain. Something that, for reasons we can't yet fathom, chose to pass through our solar system now, when we're finally capable of noticing.